Okay, good. It's gonna be a little bit less than random, but I'm gonna start by talking about quadrupole tensor, okay? Let's see here. And we'll just call all of these just examples. So I have a good idea for an exam question. So if we do this quadrupole tensor, and the best way to write it is like this. So EM, so we're integrating, I'll just say, over the body of whatever it is. So we have 3xi xj r squared delta ij. So it's best to start off with this form symbolically always, because depending on whether you have a linear, a planar, or a volumetric body, you can adjust the dm. So when we have a linear body, because I saw in one of the homework problems that it was a little confusing. When we had that linear examples, remember we have the x, y axis, z's coming out of the board, and we just have the rod from minus L over 2 to L over 2. So in that case, say we wanted to do Q11. In this case, actually, so the x3 axis is coming out of the board. Q11 plus Q22 plus Q33 equals 0. But which of those two are equal to each other? Those three, remember, it's just going to be the diagonal elements. And approaching this from the z-axis and the y-axis are the same, right? So Q22 and Q33 will be equal to each other. So it's going to be Q11 plus Q22 plus Q33 equals 0, and these two are equal to each other. So that means we only have to calculate one of them. The point I wanted to make with these elements is that in this case, that dm, so we go from minus L over 2 to L over 2, that dm is going to be a linear mass density times a infinitesimal length element. Remember, the dimension is always going to be mass. Okay? And then we've got this 3x1 squared minus x1 squared plus x2 squared plus x3 squared. Got to make these decisions as you go along. So then we realize we just have a linear body. So there will be no x2 and there will be no x3 component, right? In this particular case, to integrate over those, so those, because it's a flat, a linear body, and then the thing simplifies a lot, right? And then you take it from there. So that was for that rod, and the idea here was when you got this answer, you could compare to the ones we had done earlier by hand, so to speak. Good. So we had the linear body, then we had the ring and the disk. Okay. So the disk we'll talk about. So for the disk we had Qij. We're going to put the disk here. X1, X2. So we're going to put the disk in the X1, X2 plane. Okay. And then again, we'll always just start with the dm. We've got, I'll just write this 3 xij r squared delta ij when we fill in later. Okay. So now for the dm. We're going to integrate over the uniform disk of radius r. So this dm, I'm going to write, it's the density D area. So it's gonna be density times D area. And because it's a flat disk, this density is mass per area. Now fundamentally, this density can be a function of position. And that's what I want to pull on you guys on the exam. Make it a little more interesting. But you have to think dimensionally, so this is not a mass per volume, I'm just calling this a mass per area. Because mass per area, D area is always going to be mass. The dimension's really important here. And then you've got this. And then of course it makes sense to use plane polar coordinates, and since it was a uniform disk, then we would have the mass over pi radius squared, and then we'd use plane polar coordinates, and we would have r dr d, and then we'd have to go in here with plane polar coordinates. So now we're going to have an x1 and an x2, an x and a y. The z is suppressed because it's a disk. And I think when we, for the exam, we'll leave it in that form, right? We won't do the third dimension. Okay. Yeah, so that's, and you know, at this point, it's a double integral, and the d phi is going to go from 0 to 2 pi. dr is going to go from 0 to r. So, the pro tip here would be to know the ring in the disk. We've done both of these, right? So make sure you know the ring in the disk, and then I'll try to come up with something in between. Got some ideas. Okay. And these are the kind of thing you can always really systematically work your way through. We also had some centers of mass that we've been talking about. Center of mass, the kind that we're integrating up, so we're not going to be summing those point masses. We're doing continuous distributions. So our center of mass has 3 integrals, and you can go like this: R, dm. Always the best way to start, because depending upon whether it's linear, planar, etc. So we'll do a linear example. We had one of these on the homework. So the linear example, for say x center of mass, 1 over m, and then we would have x, and depending on the boundaries of integration, for example 0 to L, and this dm you could have rho of x dx. Okay, that would be your dm. And again, I'm just using the letter rho for density. So in this case, it's the mass per length, just like we had before, right? It's a mass per length times dx. Good. So the homework example, we had a 1 over m integral 0 to L x, and then this rho of x we said was a times x, so it was a linear dx, right? So it was a linear function. Starts out with no density and increases linearly till the end point. So the thing here was we needed an extra piece of information. We didn't know what the letter A was. Okay. But in this case, the total mass is this rho of x dx, right? That's the total mass is the dm. So in this case, it would be 0 to L ax dx. And of course, that's integrated up to a L squared over 2. Since m L squared over 2, we had A was 2m over L squared. And then, we can plug that in and continue the project. So that's the idea I have for this type of problem as well. Okay. So if I give you a mass distribution with some letter like this, you have to do the integral to figure out what that coefficient is, right? And then you can complete the problem. Good. Yeah, we have 2 hours on these final exams, so let's sit down. Do something real. Not that the other ones weren't real. So yeah, so center of mass problems, and this was one of them. Quadrupole engine problems as well. So those should be interesting. Now I can return to the couple of exams we had. Just remember what was important on those. I've got the first one and the second one. Yeah, these are fair game. Yeah, as far as the most recent stuff, what about a collision? Those perfectly inelastic collisions you guys probably found pretty easy, right? We could do one of those as well. But now I'm going to return to the early material. And I can just do variations on these problems. So if I just remind us of how these things worked out, we should be pretty good. Okay. So this was from the first midterm. And this example here, m dv dt equals minus kb, and we had b of t equals 0, b sub 0. So that was something that was sliding with linear friction law. And I also asked for the total distance traveled. So we've got this one, and remember you have dv equals minus k over m. So dv over v, k over m, dv. You integrate both sides and continue on. Okay, so those kinds, I could just come up with a different power of v or something like that. I think they're all pretty interesting. And there's even a couple little interesting twists in there. But, so you want to expect to do one of these. And remember, for the total distance traveled, you could also use this here, dv dx times dx dt equals minus kv. And in that case, this is v, so you have dv dx times v minus k over m times v. And you take it from there. At that point, you go ahead and do the same separation of variables stuff. So yeah, those two techniques, but this one is good enough, exemplifies that type of problem. We'll come up with another interesting one as well. The other problem, so this is on the first exam. The other one that is also worth doing is we had u of x equals a over x plus b times x. A and b were positive, x was also positive, so everything positive there. And then I asked for a sketch of u of x. And this is the kind of thing we like to do, recognize what a function looks like. And the way you do it on this one is you've got your 1 over x here, and you've got your b times x here. So the composite of those two, the sum of those two, looks like this. Once you're able to do that, you recognize everything. There's a local minimum, and we can carry on. Okay, so we've done that a few times. Definitely want to have skill for the final and come up with another similar like that. Number 3, I don't think we'll do period of oscillations. Well, the quadrature, so worth looking at. So we had one-dimensional problems equals E. And in fact, this would be a good one to talk about that with. Then you're able to separate variables on this thing, and what do you get? If you solve for dt, you have e minus u over x, 2 over m. Let's do a couple of steps here. So you have dx dt squared. In fact, let's leave the squared off. You have the plus minus 2 over m e minus u of x. We've seen these things a few times. So there's the velocity. The plus or minus sign has meaning. It's either going in one direction or the other direction. And this e minus u of x, if you just took this thing here and said, okay, let's let that be e. E minus u of x is the difference between the dotted line and the function. And so at the endpoints, it vanishes, and therefore those are turning points. So yeah, this analysis goes. We've seen enough of it now. So right here you can learn what velocity is, positive or negative, turning points, etc. You can also see from this picture this thing has to be an oscillation. So then you can do the solve for dt. And you've got the plus minus 2 over m here. Now this becomes an interesting integration problem. And if you integrate both sides, you get time and so forth. And if you say, okay, we're going to go from this minimum to this maximum position and multiply it times 2, that'll actually be the period of those oscillations. So that's the first time we did harmonic oscillations. We actually followed this path all the way to turning this. You guys remember what function this was for the harmonic oscillator? Integral turned into? So we had a half, if u equals a half kx squared, the integral turns into the inverse cosine. And from this process, then you ended up with omega t equals inverse cosine of x over k, and the rest is plus constant, and the rest is history. Just to remind you of the path we followed on all of this. This was the beginning of the semester. And from here, we then did the study of an oscillation, right? Linear harmonic oscillations. And then we took it into damped oscillations and everything else. So problem 4 on the first exam, that was that complex number formalism. I don't think we'll do that one on the final, because we have other things to do. But definitely, of course, I mean, this is something you guys simply know at this point. U double prime x dot over m, right? For the frequency of oscillation, of small oscillations. That's something you definitely have to have in reserve. Okay. Small oscillations. Then I'm going to go ahead and put this charged particle in a magnetic field up here on the board. Done a couple things with this one. Actually, let me go ahead and write the whole thing. QE plus QV cross V. Okay, so that is something we worked on a couple of times. Here and on the second exam, so we had done this thing in class on the second exam, I dropped the Q times E. Right, we just had Q V cross V. So yeah, this is just a good one to be able to write out what's going on very systematically, because we just have to. For example, what did I give here? Okay, from the exam, so we didn't have this one. We had R dot cross B, and we have this determinant rule calculating cross products, and I had given us next one. What did I claim for the thing? Here's what we had on the example. B equals B, some constant K hat. And yeah, that's all that's what I gave. So in that case, you would struck these two if you only had one component here, and then just systematically work out the component equations motion on it. And the thing is, they're linear with constant coefficients, so you can just systematically work your way through. So yeah, this is definitely a good one to have in your memory. Okay. Okay, then we come to what was the major focus, or the major emphasis of the semester, which was the central force problem. So let's review what we need to be able to do on that. That one actually includes all of these techniques. So for a central force problem, we have the force is a function of position, and it's of this form here. So this R is either the separation between 2 points or the separation between an origin and a mass point. So for our purposes here, say we've got the origin, we've got the vector R, length R, so that's the unit vector. So that's the first thing about the central force. The second thing is that we can get the potential energy of the central force by just integrating this f of R, which is your upper boundary. This is a constant that you can choose depending on the circumstances. For the inverse square law, take this out to infinity. Okay, so I could give a problem where you just do this step by step by step, and then what? And then we're using plane polar coordinates. So at this point, we can inherit the fact that conservation of that we have conservation of angular momentum. Okay, so we're using plane polar coordinates. And so we can write the energy as a half m r dot squared v dot squared plus q of r equals e. So that's the upshot of using plane polar coordinates, r and phi. And the conservation of angular momentum using mr squared phi dot equal to L is conserved. And we come back up here and we have 1/2 m this just goes step by step by step as well. And then what do we have here? Effective potential. And the graph of this, I'll just do the example with the Newton potential, 1 over R. The graph adds the 1 over R squared and the 1 over R. And this 1 over R squared dominates the small r, and the negative alpha over R dominates the big R. So that's where you got that. So this was for the Newton potential. And here again, we see a local minimum, so we can just use all of our techniques on this. What's the meaning of this R sub 0 though, for the orbital problem? Circular orbit. Right? So even though this is just seemingly a stationary thing, it's actually a circular orbit. And so for the circular orbit, we have this L equals M R naught squared phi dot. And since everything is now constant here, phi dot is also constant. And so I call phi dot omega sub phi oftentimes. Okay. So yeah, we can move through there. And then since we're at a local minimum, we have a frequency of radial oscillations. And we just take over what we had learned before. So this omega sub R is the effective potential of second derivative divided by the n. And if this is a two-body problem, then what is this M right here? Actually, it's the reduced mass in a two-body. Formally, it's just a one-particle problem, but it could have come from a two-body problem, and this M would have been the reduced mass. Also interesting. So yeah, we have to be able to go through with this. Thing here, I think I come up with 1 or 2 interesting ones that we haven't fully talked about yet. And the nice thing is you just take them step by step. Remember these steps, you just work through them. Figure everything out, figure it out. See what else we've got here. And of course the absolute angle, that would also be worth looking at again. A bunch of stuff here. So the absolute angle was an angle swept out by a particle that's moving between the minimum and the maximum radius of a nearly circular orbit. So it's R min, this is R max. As you would have for some energy right there. You have an R min and an R max. So because of that, there's a couple ways to express this. You could call this omega sub phi times T R over 2. So what you have is this counterclockwise constant angular speed, if you're assuming, and then you've got half of the radial oscillation period. But because omega sub R, T sub R is equal to 2 pi, you can make a substitution. You've got omega sub phi over 2, your T sub R is 2 pi omega sub R. So that's where we got this pi times didn't stop there. We did the principal calculation on this whole thing, and that turned into 3 plus r u double prime over u prime, evaluated at the circular orbit, at the radius circular orbit. So we did a couple of these. I think we've done the good ones on this. But you know, anytime we come up with the central force problem, we can ask what the absolute angle is. The ones we did for the homework were especially interesting because they were perturbations to the Kepler orbit. So the examples that were especially interesting were u of r equals minus alpha over r plus beta over r cubed, which we did. And it looked like an intractable mess down here, but what we found was for small beta, we were able to do those little series expansions. So this one was interesting. And since we've done the quadrupole tensor, we've realized that this 1 over r cubed does not extend all the way to the origin. So it's a perturbation for large r, not for small r. Okay. And the other example was minus alpha over r plus 1/2 k r squared. And in both these cases, we did k very small, beta small. Good. So these are both actually really sophisticated. This is for, say, a off spherical, oblate spheroid, where you're going to start seeing this beta. We're going to count. Okay, remember the quadrupole tensors from the disk. Next semester, when we have a little more integration skill, we'll do it for the actual oblate spheroid. And it's going to give the same kind of expression we had before, but it'll just be in terms of those parameters. So fundamentally, the disk gave this kind of thing as well. The disk and even the ring gave this kind of thing. This one comes from a solid, one of those Gauss's law things. And what its significance for astronomy is if you had a very, very dilute dust that your planets are swimming through, it would, with kind of a cosmic dust in there, then it would add this kind of a term to the potentials, and you would maybe see the signature that way. So those are good. But if we need this, I'll probably need to put this on the exam. You guys remember it, you can knock that out. So. Yeah, I'm going to remind us of that inverted cycloid problem also. Namely, the ability to work with a parametrization is important. So we could conceivably come up with some r equals r of, I'll say, tau, which describes a path. The example we had was the inverted cycloid. So we have r theta minus r sine theta. This was a vector, r cos theta minus r. And the point here is, if you want to have dynamics here, all you have to say is theta equals theta of t, and then you just have to apply the chain rule. If your derivative, you can find r dot, r second derivative, etc. In a situation like this, don't confuse this with some kind of other coordinate system. This is your x and that's your y. And this is just a parameterization in x and y. Sometimes people start using their central force formalisms in a problem like this that'll lead you astray, right? Which I'm not trying to do. But yeah, you have to just have your chain rule at hand and just stubbornly make sure you don't miss any part of it, and then you can start analyzing it. so we did one on this, so I won't use this one, but I have a couple of other ideas with parameterization. So if I give you parameterization, you want, you know, suppose I gave you a different parameterization, I wanted the energy. If this is a track, this for example, I'll just use this as an example. If this was a track here, and we have gravity pointing down, then your energy would still be 1/2 m r dot squared plus u of r. Right? And this one would be your mgy, and this one, I'm just going to write it. You'd have to calculate that, and the square, of course, is the dot product with the sum. So yeah, you would just systematically take some derivatives and work your way into an energy expression, and then you can have a look and see what comes after that. Okay, I think that's all I've got for you today. Any questions? Anybody know when the exam is?
Isn't it 8:45 Monday?
Yep, 8:45 Monday. It's always the first exam of the season. So, Monday, what date